Welcome to a video that's going to walk you through the enthalpy of a reaction lab that we did in class. The reaction that we looked at was the burning of a candle, the burning of paraffin, because that's what a candle is made of. And when we were burning this candle, we measured the enthalpy of that reaction by watching the water that was above it increase in temperature. So here's a mock data table, and in this data table you're going to want to fill in all of the missing values that are in here and then use them to find the heat that was gained by the water, the Q value, your joules that were gained by the water. Then you can use that Q value to look back at where that energy came from. It came from the heat given off by the substance here, the burning candle. Then what you're going to want to do is find your percent error. And how you find your percent error for this lab is a little bit different than what you've done in previous labs. You're going to find the absolute value of the accepted value for the enthalpy of the combustion for this reaction. You're going to subtract from that the experimental value, and you're going to find the experimental value by using these numbers, and you're going to divide this by the accepted value, multiply it times 100, and that will give you your percent error. What is the accepted value? Well, according to the internet, it's negative 42 kilojoules for every 1 gram of paraffin. Now, knowing that your paraffin is 352 grams per mole, that equates to negative 14,784, that's a kilojoule, kilojoules per 1 mole of C25H52. So we're going to use these two values, and you're going to find two percentage errors. Now they should be the same, but you're going to find your experimental value for the kilojoules per gram, and you're going to find your experimental value for the kilojoules per mole. Compare it with these two accepted values. These are accepted values from universities, and you're going to plug in these accepted values here in your experimental value, and you're going to find two different percentage errors. One for the kilojoules per gram and one for the kilojoules per mole. Try this on your own. Pause this video now. Try to find the percent error for the kilojoules per gram, and then try to find the percent error for the kilojoules per mole using your experimental values. And then restart the video and come back and watch and see if you did everything the way I did it. Hopefully we do everything the same. So we're going to erase this now, pause the video, and then come back and watch this video after you've tried your equations on your own, because we already did it once in class. And you can see if you did it right on your own for the second time. So here we go. Hopefully you've paused the video and you've restarted it now. The first thing we're going to do is fill in this cell of our data table. So we're going to take the difference of 268.7 grams, and we're going to subtract 142.3 grams. When we do that, we get 126.4 grams of water. I'm going to plug that right in here, and I'm going to use that because I'm going to find the Q value of the water. And that Q value is going to equal the mass of the water times the specific heat of the water times the change in temperature of the water. So the first thing we have is the mass of the water, 126.4 grams. The specific heat of the water, hopefully you know by now, is 4.184 joules per gram times degrees C. Now the last thing we need to know is our delta T of the water. So let's go down here and we'll skip the paraffin for a second, and let's find the value of the temperature change of the water. So what we have was 34.8, which is our temperature final. We're going to subtract from that number the temperature initial, which was 22.6. And make sure you put your units, those are degrees C. And when we do this calculation, we get a temperature change of 12.2 degrees C. So I plug this in here. I get 12.2 degrees C. And now I can find the Q of my water. And the Q of my water is positive because all of these numbers are positive, and it is 6,450 joules. So that is, I'm going to underline that in red so you can keep note of that. That is the joules, the Q value of the water. That's the energy that the water gained. The water was going through an endo process. Right? It's going through an endothermic process. So therefore, missed an S there. So therefore, energy was going into the water. Where was that energy coming from? The energy was coming from this reaction here. So from this reaction, we have heat going into the water, so we have an endothermic process for the water. It's heating up, right? The delta T is positive. All right, and I forgot to plug in my value here, but I don't have a cell, so it's fine. Now, I'm going to take this value, and I'm going to compare it, as I said, with the kilojoules per gram and the kilojoules per mole. First thing I need to do is find that value of positive 6,450 joules. 6,450 joules. I'm going to make this negative. I'm going to make it negative because I said this is a reaction and heat is being given off. So what kind of reaction is it? This is an exo reaction. Right? This is an exo reaction, not an endo reaction, because heat is a product. So let's write out that reaction really quick. That reaction is C25H52 plus oxygen gas. This is a solid, it's candle. Gives you oxygen gas plus water vapor plus, if you guessed it, heat. Heat is a product, therefore this is an exo reaction. Now if you wanted to balance that, which is not necessary in order to solve this lab, but there would be 38 oxygens required, there would be 25 oxygens, 38 oxygens. This is supposed to be CO2, my apologies. Let's get that fixed. CO2, and I'm just going to use an eraser here for a moment, get a little bit of that done. Here we go. So what you would have, I'm just going to do this in blue, is you would have 38 oxygens, you would have 25 CO2s, you would have waters, 26 waters. Again, that's not necessary to solve the equation, but you could do that. So now this becomes negative because this is an endo process and this is an exo reaction. So now it's a negative 6,450 joules. What I want to do is I'm going to turn that into kilojoules. Kilojoules divided by 1,000 joules, and what I get is negative 6.450 joules. That is how much heat was given off by the exo reaction. That's the enthalpy of that reaction, but not in any usable form. What I need to do now is I need to compare this to the grams value here of my loss of candle. The mass of the candle that was lost. I need to compare it to these two values. So I'm going to figure out how many grams were lost, which you can see was 0.2 grams. I'm going to divide that 0.2 into this number. So it was 131.4 grams, which you get right here. And I subtract 131.2 grams, and I get 0.2 grams of C25H52. That's how much of the candle was lost during the reaction. So I can go ahead and plug that in here, 0.2 grams. Now, I'm going to take that number, I'm going to take that negative 6.450 joules, and I'm going to divide it by 0.2 grams of C25H52. What you get when you divide that number is negative 16, negative 16.125 kilojoules for every 1 gram of C25H52. And then we need to just compare that. I'm going to erase this. My apologies if you saw me write joules and you're a little confused. That is kilojoules, as we said a moment ago. I'm going to compare that, right, this number here, because this is my experimental value. This is the value that we found with our experiment. If I compare that, if I find the percent error, so I find the percent error, using the accepted value from the internet, which was negative 42 kilojoules for every 1 gram. This is our accepted, as I told you earlier, value. All right, it's the accepted value here. For every 1 gram of C25H52. If I compare those two, what I'll do is I'll take the absolute value difference of this number. I will subtract this number up here, negative 16.125 kilojoules for every 1 gram of C25H52. I'm subtracting those two numbers, the absolute value difference of those, and I multiply it times 100. When I do that, I have to divide by the accepted value, which is negative 42 kilojoules for every 1 gram. And I will get a percent error of 61.6%. Okay, that's using the kilojoules per gram. And I asked you to find it in kilojoules per gram, and I asked you to find it in kilojoules per mole. So let's extend the page and we'll find it in kilojoules per mole. It's really easy. All we're going to use is dimensional analysis. So let's just block this off and say, hey, this is, over here, this is our kilojoules for every 1 gram method. And then down here, we'll do kilojoules per mole. So I take this number of the accepted value, and I'm going to convert it. So if I have negative 42 kilojoules for every 1 gram of C25H52, and I'm going to convert this into a mole. So in 1 mole, I'm going to convert this into moles because I have 352 grams for every 1 mole of C25H52. So when I do that, I end up getting negative 16,125 kilojoules for every 1 mole. Now that's my accepted value. My experimental value, I'm going to take this and convert it into moles as well, into kilojoules per mole. So what I do for my experimental value, let's just change that, let's call it EV, is I take negative 16.125, sorry guys, this is the wrong number here. Let me erase that really quick. Sorry about that if you were wondering where that math came from. It is because I had the wrong value. It is actually, my apologies, it is actually a negative 14,000. Negative 14,784 kilojoules. Alright, there we go. And I'm going to take the absolute value difference of that number minus my experimental value, which we're going to find right here. So here I have the 16.125 kilojoules for every 1 gram, and multiply it same way by 352 grams for every 1 mole of C25H52, and I get negative 5,676 kilojoules for every 1 mole. Now I'm going to take this absolute value difference, this is a negative number here, negative 5,676 kilojoules, absolute value difference of those two numbers for every 1 mole. Multiply this times 100. Divide this by the accepted value, which is negative 14,784 kilojoules for every 1 mole. Multiply all this times 100, and we get, you guessed it, 61.6%. So it's the same. It's the same value. So this was our kilojoules. Let's make this in green. We'll highlight this in green over here. This is our kilojoules per mole method, and it's proportional. So it should be the same value as when we did kilojoules per gram. So all I'm doing is dimensional analysis. I have kilojoules per gram. I'm converting it into kilojoules per mole for the accepted value and for the experimental value, and I'm using my percent error formula to find the percent error both ways, 2 different ways. All right, in the kilojoules per mole, right, and kilojoules per gram. Now, why is it so bad. Why is the percent error so high? It's because we have errors. So let's extend the page and see if it'll let me write here. What are the errors that we had? Well, if you list out the errors, they essentially fall into one big category. The errors, if you list them out, you can think of 5 right off the bat. They essentially have to do with heat was lost to, and then you fill in the blank. Essentially, these are all the same. Heat was lost to where? And then you just tell me where it was lost to. So one place, obvious, is the air, right? When you look up here, you're saying, well, the heat wasn't going right into this water. Some of the heat went off into the air. So yeah, so you lost energy from the reaction. Where else did the heat go? It went into the glass of the beaker, right? That was a place. Where else did it go? It went into the glass, the watch glass. The watch glass was that little piece of glass that the candle was sitting on up here. This is the watch glass. Heat went into that. Where else did it go? It went into the mesh wire. That mesh wire that the beaker was sitting on. That mesh wire gauze is what they call it, right? It went into that. It went into this mesh wire gauze up here. Where else did it go? It went into this metal ring, right? It went into the metal ring. And last but not least, it went into the melted wax. So this is the most thoughtful error, I would say, is the melted wax. And the reason that I would say it's thoughtful is because you are looking at the amount of wax that was burnt, that was turned into gas. So this wax here, I'm just going to try to highlight this for you. Right, this wax here was turned into gas. It was turned into CO2 and H2O. And it also turned into heat, right? But what about the melted wax? The melted wax was kind of caught on this watch glass. That's why we measured it with the watch glass before and after. So what we're doing here is we're saying some of it, the melted wax, it went through a process. It went through a process, and I would say the wax that went through a process. Let's get on this page a little bit. It went through a process, a melting process of melting, right? And that is different than going through combustion. So what you found up here was your percent error for the enthalpy of combustion. So here's your value. This is your experimental value for the enthalpy of combustion. Right here. Right there. That's what it is, right there. That's your experimental value for the enthalpy of combustion. Also, right there. Right? In kilojoules per mole and in kilojoules per gram, just different units. Moles of what? Moles of paraffin, C25H52. So that is the enthalpy of combustion, your experimental value. What you did was you compared it to the actual value that you found on the internet. You found that you had a really big error. You had 61% error for both, 61.6% error for both kilojoules per gram and kilojoules per mole. Why? It's because we lost so much heat to the air, to the glass, all these things, and also to the melted wax, because the melted wax went through a process. And again, how did we calculate this value of enthalpy of combustion? We used water. We used an endothermic process for water. We knew the specific heat of water, the mass of the water, the temperature change of the water, so we were able to get an energy value, a joules value, for the energy gained by the water. Water gained heat because it was an endo process. Burning of this candle was an exo reaction. It gave off heat. Now, if you're going to do this in real life at a lab, what you're going to use is a device like this. You're going to use a device like a bond calorimeter, such as these devices here. So in this device, if you're working, let's say, for a food company, you put the sample, either candles or cookies or whatever you're burning in here, You ignite it with these wires. You supply it with oxygen so it can burn. Surrounding it is water. There's a thermometer to measure the temperature change of this water, and even a stir so that way the heat is uniformly transferred around the container. This is called a bomb calorimeter, and this is how people measure the energy, the joules, or the calories that are contained within a snack or within a candle, any substance that you can burn. So when you go to the store and you see that, oh, this cookie has 70 calories per cookie, what they measured that with is this kind of device, a bomb calorimeter. They burned it. They measured the temperature increase of the water. They used the same calculations that you used here in your lab, right? They used the same calculations that you did here, the Q of the water. Then they took the grams and they divided the energy by the grams, and they got experimental values, and then they did it over and over and over again until they got an accepted value. And that's the process that you guys did here for the enthalpy of combustion for the paraffin. Alright, hope you learned something from this, and you can take it into real life looking at a food label from now on, and you can use this also for your quiz or test or future labs.